Basics of High-Frequency X-ray Generator. This tutorial is presented by Arindam Sarkar. High-frequency X-ray generators are being used to an ever-increasing extent. This tutorial is intended to provide a means of access to the comparatively newer technology. It is dedicated to all those who are familiar with technology used for the conventional line-frequency X-ray generators. To make the subject less complicated, a detailed description of the circuit arrangement has not been included. Here you will be introduced to the converter technology, or more precisely the series resonant converter that plays the pivotal role in the high-frequency X-ray machine. We will start with a brief discussion on both the line frequency and high-frequency X-ray machines with the aid of their block wiring diagrams to identify how the newer technology differs from the conventional technology, and then move forward to discuss the fundamentals of the high-frequency X-ray generator. The semiconductor switching device used as examples in this tutorial are thyristors. However, nowadays other power semiconductor devices such as MOSFETs and IGBTs are commonly used as switching components in high-frequency X-ray machines. Line frequency X-ray generator. This block wiring diagram is generally applicable, irrespective of whether the X-ray generator is a modern type with microprocessor control or a primeval conventional generators. The mains voltage is passed on via the on circuits, that is, a contactor and an automatic circuit breaker, to the step transformer or a carbon roller transformer. This transformer delivers the primary voltage for the high-tension transformer. The primary voltage is applied to the high-tension transformer via a timer which may comprise either contactors or thyristors. In the high-tension transformer, the primary voltage is stepped up to the desired level of 35 to 150 kV. The output side is provided with arrangements for rectification and filtration of the high tension. The load is the X-ray tube. Fluoroscopy. Fluoroscopy has a power circuit of its own. kV and MA can be controlled separately. For this purpose, most high-tension generators have a separate winding. Filament circuit. For operation of the X-ray tube, the cathode has to be heated, which occurs via a filament circuit. The filament circuit may be a network of resistors connected to 220 volt or a switching network. Rotor control. The rotor control ensures that the anode disc of the tube starts to rotate and reaches a specific speed within a predetermined period of time. Control. All components are supervised and checked by a control system which may be based on the use of relay circuits, transistor circuits with digital and analog integrated modules, or in some modern generator, a microprocessor. High-frequency X-ray generator. The introduction of high-frequency technology causes a few essential alterations in the block wiring diagram. Now the converter block takes the place of the step or carbon roller transformer and the timer. From the converter, an AC voltage with an increased frequency in the range of kHz is passed on to the high-tension transformer, the output of which is also equipped with rectifiers and filter sections. The high-tension generator feeds the X-ray tube. Fluoroscopy. When watching fluoroscopy, you will also realize a difference. The fluoroscopy unit has now been partly integrated. It consists of no more than a few control circuits. For the X-ray generator, a fluoroscopic exposure corresponds to a radiographic exposure with a very low load and a very long time. Filament circuit. The filament circuit has also been set up according to the principles of converter technology. Rotor control. The rotor control has been partly integrated in the high-tension converter. This means that parts of the power electronics are used twice. Rotation of the anode disk occurs in the phase of preparation. High tension is generated during the exposure. Technically, this is a smart solution which was adopted for the few HF X-ray generator. However, other generators continue to be provided with separate rotor controls. Control. The control of the high-frequency X-ray generator is essentially identical with that of the line-frequency X-ray generators, having soft-touch controls. Some of the controls additionally includes the selection option of pre-programmed exposure techniques based on the anatomy to be examined. This feature is called APR, anatomically programmed radiography. The use of a converter brings about a significant change in the design of high-frequency X-ray machines. So, we will briefly discuss what does a converter do and what is the advantage of using this technology in high-frequency X-ray machines. A converter in a high-frequency X-ray generator converts the frequency of the mains AC power supply from 50 Hz to higher frequencies, typically in the range of kHz. The mains AC of 50 Hz is rectified to DC and then converted back to AC in range of kHz. The mains voltage of 50 Hz is passed on to a rectifier bridge so that a DC voltage with a low ripple is available at the output. The DC voltage is smoothed by the capacitors. Another object of the capacitors is to absorb a return current from the oscillator circuit. The block that follows is the converter itself. It consists of 2 or 4 thyristors. A detailed description of their function will be given later. The output of the converter is connected to a load which is fed with an AC power supply in the range of kHz. The illustration to the right shows the waveform of the voltages at the different stages in the converter. Now that we have discussed the role of the converter in high-frequency X-ray generators, let's explore the advantages of using high-frequency X-ray machines. There are several advantages of high-frequency X-ray generators over conventional line-frequency generators. Increased efficiency. High-frequency generators use solid-state power switching technology, which is more efficient than the relay-based switching used in conventional generators. This results in less power loss and higher efficiency. Compact design. With the increase in frequency, the core size and the number of turns of the coils in the high-tension transformer is considerably reduced, reducing the bulk of the transformer. Also, the solid-state components used in high-frequency generators are smaller and lighter than the components used in conventional generators. This makes the generators themselves smaller and lighter, which can be particularly beneficial in mobile X-ray applications. Improved image quality. High-frequency generators can produce X-rays with a more consistent energy spectrum, which can result in better image quality. This is because the energy spectrum of the X-rays is less affected by fluctuations in the power supply. Reduced radiation dose. High-frequency X-ray generators can produce X-rays with a more precise energy spectrum, which can be tailored to the specific imaging needs of the patient. This can result in lower radiation doses for patients. Higher production rates. Since high-frequency generators use solid-state devices in the power circuit, they can produce X-rays at a higher rate than conventional generators. Also, the reproducibility of the X-ray output is more consistent. This can be particularly beneficial in busy medical centers, where there is a high demand for X-ray imaging. In this introduction section of the tutorial, we have learnt about converter, where it is used in the high-frequency X-ray machines, what is its function, and what are advantages associated with its use. From here we move on to the fundamentals of the converter. The converter in the high-frequency X-ray generator is a so-called series resonant converter. The converter uses a series resonant circuit that consists of an inductive element, L, and a capacitive element, C, which are connected in series. The current and voltage characteristics of these elements will be discussed in this section. We will start our discussion with RC circuit followed by RL circuit. Thereafter, we will move on to the discussion on series resonant circuit that consists of a RLC circuit and forms the heart of the series resonant converter. RC circuit. The illustration on the left shows a simple RC circuit. The illustration on the right shows the current and voltage characteristic on an RC circuit. A DC voltage UE is applied to its input at the moment t0. The immediate response obtained at the moment t0 is a high current I across the capacitor C. The capacitor is practically a short circuit. The current I is limited by resistor R. At the first moment, the voltage you see at the capacitor is 0 and then rises according to an E function. The current I drops according to an E function, and after about 5 tau it is about 0 and UC has risen to the applied voltage UE. Tau is the time constant of the RC circuit and is derived from the product of R multiplied by C. RL circuit. The illustration on the left shows a simple RL circuit. The illustration on the right shows the current and voltage characteristic on an RL circuit. A DC voltage UE is applied to the input at the moment t0. As a result, a current starts to flow in the inductor L. It builds up a magnetic field, which counteracts current I. So the inductor represents a high resistance at the moment t0. At the first moment, the voltage UL at the inductor is same as the applied voltage UE and then drops according to an E function. The current I rises according to an E function, and after about 5 tau it reaches its maximum, limited by resistor R, and UL drops to 0. Tau is the time constant of the RL element and is derived by dividing L by R. Let us summarize our learning on the current and voltage characteristics of RC and RL circuits discussed so far. When connected to a DC power supply, both RC and RL circuits exhibit a transient response in their current and voltage characteristics. The transient time is approximately 5 times the time constant. and the value of the time constant depends on the value of the elements used in the circuit. After the transient time, the current and voltage in the circuit goes to a steady state. Let us summarize the transient responses of the RC circuit and RL circuit in a tabular format. From this tabular summary, we can easily make out that the responses of RC and RL elements are contrasting in nature. You may pause here for a while to take note of the details in this table. Next, we will learn about the current and voltage characteristics of these two elements when connected in series to a DC power supply. Here, we will find how the contrasting responses of RC and RL elements enable the repeated exchange of their stored energy between themselves, resulting in an oscillating current and voltage output. Series resonant circuit. The illustration on the left shows a series connection of the RC and the RL elements. A series resonant circuit of L and C is obtained, with R essentially representing the copper resistance of coil L. The illustration on the right shows the damped sine wave oscillation of the voltage UC across the capacitor C, represented by the dotted line. The damped sine wave oscillation of the current I in the circuit is represented by a continuous line. The DC voltage UE is applied to the input at the moment T0. The capacitor is practically a short circuit. The current increase is limited by the inductor coil L. At the moment T1, the voltage on the capacitor is equal to the voltage UE applied. The current I is at its maximum. The inductor keeps the current from changing abruptly to zero. After the moment T1, the current turns gradually to be lower and approaches zero. But as the current flow is still positive, the capacitor is practically overcharged. Voltage UC turns to be higher than the input voltage UE. At the moment T2, the voltage UC on the capacitor has reached its maximum. The current in the circuit is now zero. The voltage applied on the capacitor UC is now more positive than UE, the input voltage applied. So after the moment T2, the capacitor C discharges again via the inductor. The result is a negative current. At the moment T3, the capacitor voltage UC is equal to the applied voltage again. Once more, the inductor L prevents the current from changing abruptly to zero. After the moment T3, the capacitor continues being discharged. At the moment T4, the voltage UC has reached its minimum, the current has crossed zero. The oscillation generated is damped more or less depending upon the value of R. After an infinitely long period of time, the oscillation has decayed so far that the current I is zero and the voltage on the capacitor is equal to the applied voltage UE. The frequency of the oscillation is determined by the value of the inductor L and the capacitor C. Now, if it is possible to change the polarity of the supply voltage each time the current crosses zero, that is, if the polarity of the supply voltage applied to the series resonant circuit changes at the moment T2, T4, T6, the oscillation obtained is not a damped but a continuous one. The result is a sine wave oscillation. The frequency is determined by L and C. Current and voltage are in phase quadrature. Next, we will study the series resonant converter, which uses a bridge circuit to change the polarity of the voltage applied to a series resonant circuit. This section of the tutorial will cover two types of series resonant converters, the full bridge circuit and the half bridge circuit. The semiconductor switching device used for description of the series resonant converter in this tutorial are thyristors. However, nowadays other power semiconductor devices such as MOSFETs and IGBTs are commonly used as switching components in high-frequency X-ray machines. Series resonant converter. Full bridge circuit. The illustration shows the wiring diagram of a series resonant converter. An AC voltage of 50 Hz is applied to the input. This AC voltage is supplied to a rectifier bridge via a contactor. The DC voltage appearing at the output of the rectifier bridge supplies the capacitors C1 and C2. This DC voltage is transmitted to the four thyristors TH1 through TH4. The series resonant circuit consisting of capacitor C and inductor L is located in the middle of this bridge. The thyristors TH1 and TH4 are made to fire. Now the conditions obtained are those previously prevailing in the series resonant circuit we discussed earlier. Application of the DC voltage to the resonant circuit causes the same response as described therein. The current flows from plus to minus through thyristor TH1, capacitor C, inductor L and thyristor TH4. The thyristors TH1 and TH4 are blocked while the current is crossing zero. They are not capable of conducting a negative current. The current flow changes its direction and now flows from minus to plus via diode D4, inductor L, capacitor C and diode D1. The force driving this current is the energy stored in the capacitor C, which is now overcharged. The energy is picked up by the capacitors C1 and C2 because the 6 diodes of the power supply unit are blocked for this direction of current. For technological reasons, the thyristors TH2 and TH3 can fire only a few microseconds after zero crossing. For this time, that is, the so-called recovery time, the flow of current is taken care of by the diodes D1 and D4. The recovery time is the time required by the thyristor to change from the conductive to the blocked condition, plus a certain safety margin. When the thyristors TH2 and TH3 fire, the current stops choosing the path through D1 and D4. The current now flows from plus to minus via TH2, inductor L, capacitor C and thyristor TH3. When the current crosses zero again, the current is first taken over by the diodes D2 and D3 and, after termination of the so-called recovery time, the thyristors TH1 and TH4 are made to fire again. This procedure can be repeated as frequently as desired. Summarizing the sequence, we can say that for the time during which TH1 and TH4 were conductive, the series resonant circuit was connected to the capacitor with plus and the inductor with minus. Now, after TH2 and TH3 have become conductive, the capacitor is connected to minus and the inductor to plus. This fulfills the condition for continued oscillation, that is, the change of the supply voltage polarity to the series resonant circuit at each zero crossing of the current. The illustration on the right shows the current characteristics after firing of thyristors. Next, we will discuss the intervals between thyristor firing and its effect. At the beginning of this tutorial, it was pointed out that the converter provides the possibility of high-tension control. To understand this function, let us refer to this illustration for intermittent operation. Unless the thyristors TH2 and TH3 are caused to fire immediately after the current crosses zero, the situation is the one represented. For some time the current flows through TH1 and TH4 and afterwards through the diodes D1 and D4, then it turns to be zero. The effective value of this current decreases as the time t increases, that is, the intervals turns to be longer. The frequency with which the thyristors are made to fire is termed repetition frequency or F-rep. The more the repetition frequency rises, the more the effective value of the current rises, and so, the secondary end charge of the high-tension capacitor, that is, the high tension applied to the tube. In this situation, a control loop has only to vary the time t. The voltage provided to a load can be controlled between a value as low as desired and the maximum value. The illustration on the right is a simplified representation of the current in the oscillator circuit, showing the transmission of the maximum output. Next, we will discuss about the half-bridge circuit. Series resonant converter, half-bridge circuit. The illustration shows half-bridge circuit, where two thyristors are used instead of four. This series resonant converter works according to the same principle as previously described for the full bridge. The object is also to change the polarity of the voltage on the series resonant circuit. For this purpose, the DC voltage is divided into two equal part voltages by the capacitors C1 and C2. The reference point for the voltages is located in the middle between the two capacitors. If measured with respect to the reference point, a positive voltage is applied to C1 and a negative one to C2. The two voltages should be considered as two separate voltage sources. When the thyristor TH1 fires, a current flows from plus end of C1 to the reference point, that is, to the minus end of C1 via thyristor TH1 capacitor C and inductor L. After the current crosses zero, it stops flowing through thyristor TH1 and now flows in reverse direction through D1. It now flows from minus to plus of C1 via the inductor L, the capacitor C and the diode D1 and charges capacitor C1. After termination of the recovery time, thyristor TH2 fires. The direction of the current through the series resonant circuit remains the same, but the current path switches to the reference point, that is, plus end of C2 to minus end of C2 via the inductor L, the capacitor C, and the thyristor TH2. Now the circuit works practically with the second voltage source C2. When the current crosses zero, thyristor TH2 stops being conductive and the current is taken over by diode D2. Now the thyristor TH1 can fire again. This procedure can be repeated as frequently as desired. When TH1 is conductive, the voltage applied to the capacitor C is positive and the inductor L is negative. After TH2 becomes conductive, the voltage applied to the capacitor C is negative and the inductor L is positive. This causes a change in polarity of the voltage applied to the resonant circuit. In this case, too, the transmittable output can be controlled in exactly the same way as with the full bridge, that is, by changing the repetition frequency. The illustration in the top right-hand corner depicts the flow of current following the firing sequence of the thyristors and through the diodes following the zero crossing during the recovery period, before the other thyristor fires. Now that we have learned about the series resonant converter, let us explore how this converter technology is implemented in high-frequency X-ray generators. The principle of the converter described so far is utilized at different points in high-frequency X-ray generators. In some generators, the high-tension AC output is rectified by a full bridge, while in other generators a half bridge is used for this purpose. In most high-frequency generators, two half-bridge converters are used to generate the current in phase quadrature for the rotor control. Similarly, for the filament circuit, half-bridge converters are used for each focus control. Generation of high tension. The illustration shows the converter for HT generator. An important point to note is that the converter for high-tension generation does not use any inductor coil. The primary winding of the high-tension transformer, or, more exactly, the leakage inductance of the high-tension transformer, plays the role of the inductor. If the resonant current flows through the primary winding of the high-tension transformer, a voltage is induced in the secondary winding. This voltage is rectified and charges the capacitor C. The tube current causes the capacitor to be discharged. The ignition frequency of the thyristors determines the magnitude of the voltage at the tube. The illustration on the right graphically represents the plot of the tube voltage against thyristor ignition or firing interval. Apart from the remarkable advantage to control the voltage at the tube effortlessly by changing the repetition frequency, this technology ensures a considerable improvement of the constructional features of the high-tension transformer. Previously, a 50 kilowatts high-tension transformer had a total weight of 360 kilograms, while today its weight is 80 kilograms. The copper weight has been reduced from 45 kilograms to 2.4 kilograms. Ripple in waveform of high tension. In the X-ray generators, the form of the high tension has so far essentially been determined by the kind of the rectifier circuit in the HT generator. The illustration shows the ideal form of high tension in 2, 6 and 12 pulse line frequency generators. The lowest ripple was obtained with the 12 pulse circuit arrangement. Though the 12 pulse ripple is very low, the non-symmetry of the mains and pronounced voltage drops cause it to increase as loads turn to be higher. The ripple of a 12 pulse generator amounts to approximately 12% in the case of full load. In high-frequency generators, the dependence of the ripple upon the load switched is exactly inverse. In exposures with high loads, the repetition frequency is higher than in exposures with low loads. So, the ripple turns to be lower as tube currents increase. For instance, it's approximately 14% at 80 kV and 50 mA and approximately 5% at 350 mA. The ripple does not depend on the mains frequency but on the converter circuit and the desired output. Rotor control. The converter bridge consisting of the thyristors TH1 through TH4 and the diodes D1 through D4 can be switched over from the series resonant circuit for high tension, that is, C1L1 to the two resonant circuits for rotor control, that is, C2L2 and C3L3. L2 and L3 are the stator windings of the tube assembly. C2 and L2 form a half bridge together with the thyristors TH1 and TH3 and the diodes D1 and D3. A second half bridge is formed by C3 and L3 with the thyristors TH2 and TH4 and the diodes D2 and D4. The half bridge is fed with part voltages via capacitors C4 and C5. C4 feeds the power when TH1 and TH2 fires. C5 feeds the power when TH3 and TH4 fires. During the standby and the preparation stage for high-speed acceleration of the rotor, the converter of the generator is connected as a rotor control. The thyristors TH1 through TH4 are caused to fire by initiation of preparation. Now two half bridges are working independently of each other, with a phase control making sure that the inductance L2 and L3 provide the stator with a rotary field. A contactor provides for changeover at the end of the preparation. The capacitors C2 and C3 and the inductance L2 and L3 are switched off. C1 and L1, that is, the high-tension generator, are connected in the circuit instead. Now the converter is ready to generate high tension. At the end of the exposure, that is, the generation of the high tension, the contactor changes back to the rotor control circuit for breaking the rotor and standby condition. In this way, the thyristors TH1 through TH4 and the diodes D1 through D4 are used for two purposes. On one hand, to start anode rotation and, on the other, to generate the high tension for radiography and fluoroscopy. However, many other high-frequency X-ray machines use a separate and dedicated converter for rotor control. The principle of operation described here remains the same, excepting the switchover of the contactor. The filament circuit. In most of the high-frequency generators, the filament circuit has been designed on the basis of converter technology. The mains voltage of 220 volt is applied to C1 after rectification. Thyristor TH5 is a so-called crowbar thyristor. It protects the elements that follow. In the case of a fault in the power supply, it is caused to fire and short-circuits the power supply unit, making sure that the series-connected fuses respond, so protecting the electronic system that follows. The filament circuit has a half bridge for the small focus and a half bridge for the large focus. The half bridge for the large focus consists of thyristor TH1 and TH2, diodes D1 and D2, inductor L1, and the capacitors C2 and C3. The use of two capacitors, that is, C2 and C3, is somewhat different than that of the half bridge of the rotor control. Half the DC voltage of C1 is applied to each of the capacitors C2 and C3. Under the DC voltage aspect, the capacitor C1 has to be considered as a short circuit. So the effective capacitance for the oscillator circuit is the parallel connection of C2 and C3. The half bridge for the small focus consists of the capacitors C4 and C5, the inductor L2, the diodes D3 and D4, and the thyristors TH3 and TH4. During the standby condition, the half bridge fire at very low frequency to supply preheating current of the selected focus. This firing frequency is controlled by a filament current regulator. During the preparation, the selected focus is boosted by increasing the ignition frequency of the respective half bridge. The filament control circuit controls the ignition frequency depending on the set MA. During the exposure, the tube current control circuit takes over the control to send feedback of the measured actual tube current to the filament control circuit. The ignition frequency is varied or kept constant by the filament control circuit to maintain the desired tube current. We will discuss about the filament control in the next topic, the generator control circuits. With the use of smaller and lighter components along with digital signal processing and microcontrollers in modern high-frequency X-ray generators, it is easier to integrate control circuits into the high-frequency X-ray generators. Moreover, with the use of high-frequency switching devices, such as thyristors, IGBTs and MOSFETs, enables the control circuit to quickly respond and adjust the X-ray output by regulating the current and voltage supplied to the X-ray tube. The implementation of control circuits provides more precise and flexible control over the X-ray output compared to older analog control systems used in line-frequency X-ray generators. Before we get into the description of the generator control circuits, let us start with an overview of control of high tension in particular. Control of high tension. So far, the converter circuit was presented only as an open-loop control. If a feedback system of the actual output value is integrated in the system to control the output to a set value, you obtain a closed control loop. The illustration shows a converter full bridge with HT transformer, rectifier, smoothing capacitors and X-ray tube. The ignition control circuit is supplied with the set point for HT, that is the kV value, and tube current, that is the MA value. Already we learnt that with increase in load, that is tube current, the firing frequency of the HT converter needs to be increased. This is required to maintain the desired HT output. Therefore, along with the HT set point, the tube current set point is equally important to set the working point of the ignition control circuit. The HT measurement circuit is fed by the two potential dividers connected at the HT supply point of the anode and the cathode. The output of the HT measurement circuit is proportional to the generated HT. During the exposure, the output of the HT measurement circuit provides the feedback signal to the ignition control circuit. A comparator in the ignition control circuit compares the feedback value with the set point value. The difference of these two values is the error signal. This error signal is fed through an amplifier to adjust the firing frequency. By varying the ignition frequency, the control circuit with ignition frequency control provides for a constant tube voltage. If the tube voltage changes due to alteration of the tube current or an unstable mains voltage, the actual value obtained via feedback is subject to a change. The ignition frequency control varies the ignition frequency so that the tube voltage is kept constant. The generator control circuits. Though this illustration is a simplified representation of the control loops of a particular model of high-frequency generator, other models of high-frequency generator have control loops much in common. At standby, the computer delivers the HT set point to the high-tension regulator, and the tube current set point and the filament current set point to the tube current regulator. The filament current set point corresponds to the value required for preheating the filament. The converter has been connected such that the rotor control can be activated immediately upon initiation of preparation. At the beginning of preparation, the anode rotation is started and afterwards the converter is changed over for high-tension operation. Now the filament current set point for the expected filament current of the exposure is delivered. The feedback from the filament current actual value ensures that this filament current is available. The tube current set point is passed on to the HT regulator. It is required for adjusting the working point of the converter power assembly. An exposure is released. When the high tension reaches 75% of its set point, this is the time at which radiation is started. At this moment, the regulator is changed over from filament current to tube current regulation. It is no longer the filament current that is controlled, but the actual value of the tube current is measured and compared with the tube current set point. The difference signal is the deviation which is adjusted to 0. The high tension is measured, the value measured is compared with the set point issued by the computer, and the difference signal is the controlled variable, with which the repetition frequency is varied. In this way, the high tension is varied or kept constant. The above procedures and control actions for current and voltage at the tube have much in common with those of the other make and models of high-frequency generators. Key takeaways from this tutorial. High-frequency X-ray machines use converter technology. The converters are used to convert the mains frequency of 50 Hz to the range of kHz. High-frequency X-ray machines have many advantages over the line-frequency X-ray machines. The converters used in high-frequency X-ray machines are series resonant converters. Series resonant converters use a bridge circuit to switch the DC power supply to the LC circuit at each zero crossing of the resonant current. Both full bridge and half bridge converters are used in the high-frequency X-ray machines. Full bridge converters are used for high-tension generation and half bridge converters are used for rotor and filament control. The firing frequency of the thyristors controls the effective output current. Control circuits are used to monitor and control the actual output value against a set value. Thank you for watching this tutorial video on basics of high-frequency X-ray generator. I hope you found it helpful in understanding the topic covered here. If you have any questions or feedback, please feel free to leave them in the comments section below. Your suggestions will help me create more informative and useful content in the future. Thanks again for your time and attention.